today's first topic are the laws of thermodynamics. The laws of thermodynamics is this set of 4 laws that the whole universe follows that have to do with heat and heat energy and temperature. So we're going to go over each of them and some definitions that are going to come out of them. So the first law in the list of laws is actually called the Zeroth Law. So like Zeroth Law. And it's called like this because there were originally 3 laws, but then they thought about this law and they said this one is more fundamental and more basic than all of the other laws. But instead of renaming all of them to the following number, they just decided to create Law 0. So there's the Zeroth, first, second, and third law. So the Zeroth Law of thermodynamics is something that seems very logical, that it makes sense, but it's very important and fundamental. So what it says basically is that if you have an object A and an object B and an object C, whatever they are, and object A and object B have the same temperature, so the temperature of A is equal to the temperature of B, and also B and C have the same temperatures, so the temperature of B is equal to the temperature of C, that means that the temperature of A and C must also be the same. So that means that the temperature of A is equal to the temperature of C. So that's pretty obvious. Let's say both A and B are at 20 degrees. 20 degrees Celsius, 20 degrees Celsius. And B and C are also the same. So 20 degrees Celsius and 20 degrees Celsius. What the law states is that A and B are also the same. So they're both also at 20 degrees Celsius. And this sounds really basic, almost stupid, because it just makes sense. It's obvious. But it was very important for scientists and for physicists to cite this law because it's what allows us to have thermometers. Because when we measure something with a thermometer, the thermometer, and you put it inside a glass of water, you have to assume that the thermometer and the glass of water are going to reach thermal equilibrium before the temperature of the thermometer, the temperature it says inside, is the same as the temperature of the water. So that's why you have to wait until thermometers reach thermal equilibrium with whatever you want to measure so that the temperatures are the same. But that's just the first law, very basic law. Now the first law of thermodynamics is one that we've heard before many times. I think I've told you this law before in class and you've probably heard it just being said. And it's that energy is not created or destroyed, it's only transformed. So let me write that down. So energy can't be created or destroyed. Created or destroyed, only transformed. And that means that the energy of the universe as a whole is always going to be constant. So the energy that came out of the Big Bang is exactly the same total amount of energy that we have in the universe today. That doesn't mean that a system can't change its energy. If I throw this pen, it's going to be moving faster and have more energy than if I hadn't thrown it because I gave it some energy. But in total, I had to transfer energy to the marker so that it moved, and I lost some energy in the process. So all the energy in the universe is constant. So that's what that law means. But it also has a more thermodynamic and a mathematical way of being expressed. So for that, we're going to need to define a couple of concepts. Well, some we already know. So let me see. So we've been talking throughout this whole unit of heat, and heat is given the letter Q. We know that already. There's something else that we looked at last year at the end of the year that was work. It's this type of energy that moves things, right? So we have work. So W is work. You guys know about it. And there's another concept that is called internal energy, and we call it delta U. This is internal energy. So we'll change in internal energy. So what is internal energy? Internal energy is when we have a system, the total sum of energies of the system. So all the energy that it has inside. So it's the total energy inside a system. So the way in which these three concepts are written as an equation that means the same thing as energy can't be created or destroyed is that if the energy inside a system changes, something had to change it, because energy just doesn't create or disappear out of nothing. So if there is a change in the internal energy of a system, it must be because one of two things. One is if heat was put into it. So we have a pot of water, and it's just lying there. It has some internal energy. How can we increase the internal energy? Maybe by increasing the temperature, right? So we could do that by adding heat. So the internal energy is going to change if we add heat. And something else that could change the internal energy of a system is if we do work on it. So if we add the work that we do on it plus the heat that we put into it, that amount is what is going to change the internal energy. So internal energy in thermodynamics, internal energy is proportional to the temperature of the system. Proportional to T, the temperature of the system. Why? Because the energy is in the molecules, and it can be measured by how much the molecules are moving, how fast they're moving, if they're colliding. And if you increase the temperature, we have seen that the molecules will start moving faster, so they'll gain internal energy. So the higher the temperature, the more internal energy it has. So you can basically increase the temperature of a system by putting some heat into it or by doing work on it. So by moving it, we're going to see some examples of how this can happen in the following video. So this is basically the equation that expresses the same concept as energy can't be created or destroyed, only transformed. And it's another way to write the first law of thermodynamics. We're going to use it a little bit later. So that's the first law. What about the second law? The second law of thermodynamics includes a new concept for you probably that is called entropy. Maybe you've heard about it before. And the law states that the entropy of the universe is always increasing. So the total entropy, and it's written like this, entropy of the universe can only increase. So what is entropy? Entropy is many times described as the amount of disorder, how disorganized something is. So entropy, let's define it like that. Entropy, amount of disorder. So when some people explain the second law of thermodynamics, they use the example of a dirty room. So if you have your room at your house and you leave it there, it won't organize itself. You have to actually put in some work to organize your room. If you leave it there, it's going to gain dust, maybe your little brother moves something, and in general, if you don't do any work, it's going to tend towards more disorder. So the entropy of your room will only increase. The disorder of your room will only increase if you let it be. You need to actually put in some energy to go in the other direction, to decrease the entropy of your room. And another way that I really like to describe entropy is that there is only one situation that can be called order and many of disorder. So for example, you buy a deck of cards and the deck of cards comes organized. So it's ace, 2, 3, 4, 5 of one stick and then the other one, and it's organized. When you shuffle it, it's going to be disorganized. So it's going to have more entropy than before. And there are many, many, many ways in which the deck can end up being organized, but it's always going to be in disorder. It would be very, very improbable that you shuffled the deck of cards and you ended up with perfect order, the order it came with. Because there are many more possibilities of disorder than order, then usually everything tends towards getting disorganized instead of getting organized. You can also see this if you were to film yourself and you throw some salt and then some pepper into a jar. When you see them first, the salt is below and the pepper is on top because you put in the salt first and then the pepper. You get the jar and you move it around, and the pepper and the salt are going to mix. Then if you were to show that video to your mom backwards, so you put the video in reverse. So first you have salt and pepper in a mixture, and you moved it around and they separated into a film of pepper and a film of salt. Do you think your mom is going to notice that the film is backwards? Of course, because that never happens. You never mix something and it becomes unmixed. It separates into perfect layers. That's because there's only one way in which the molecules can be organized for it to be order, and thousands of millions of ways for it to be disorder. So this is also called the arrow of time, because if we put the movie backwards, we would see things getting organized, or instead of a cup being dropped and breaking, we would see a broken cup coming up and being fixed by itself and lying there on the table again. So that's how we express the entropy of the universe always increasing. And the third law is also a bit weird because it has to do with entropy, but it basically states that the only way there can be an entropy or a disorder of zero is at absolute zero. So maybe you remember at absolute zero, which is 0 Kelvin, the lowest possible temperature theoretically, so 0 Kelvin. At absolute zero, the entropy is 0. Because as I had told you some classes ago, at 0 Kelvin, nothing is moving. All of the molecules are absolutely still. There is no temperature, there is no motion, so there can't be any disorder. This is the only situation in which it happens, and 0 Kelvin has never actually been reached. So basically what this means is an entropy of 0 is impossible. And this one says the total entropy will always tend towards increasing. So these are the 4 laws of thermodynamics.